Back to effect of air resistance. So yeah, like I was saying, obviously in real life, a falling object will encounter air resistance because in real life it's not vacuum. Okay. Yeah, air resistance, what is it? It's basically a force that acts against the motion of the object, right?
Yeah.
If we write it down, against the motion. To reduce its downward acceleration, not speed. Okay, I'm going to write it in red. To reduce its downward acceleration to 0. Okay. Yeah. So let's say this is a falling object, just falling with G above. That's where we have our air resistance working upwards. Yeah. Now, when the air resistance increases, no, the air resistance will increase till it is equal to the weight of the falling object, okay? So,
But we don't have the control over air resistance, right? Like how much resistance it's giving.
sorry?
Like you said, air resistance will increase or decrease when it becomes equal to the gravitational acceleration. We don't have the control over the air resistance, right?
Yeah, we don't have any control over it. We can actually, for example, you learn like obviously the design of a parachute. It is designed so that the air resistance is increased. I mean, if you have like a large surface area and stuff like that, that will increase the air resistance. Yeah, yeah, we have some control over it, but not necessarily after, let's say, we jump. Okay.
Yeah. Yeah.
So I was here. Now, what happens when the acceleration becomes 0? The object will fall at a constant velocity, right? This is known as the terminal velocity. Okay. Okay, that's it. So, like I mentioned, air resistance is a force, which I made a small mistake. The downward force, because of the gravity will be mg, right? This is the weight of the object. Okay, so the air resistance will keep on increasing until it equals the weight of the object. Okay.
Yeah.
All right, now we will do an example. Okay, I'll try to bring this on my iPad just a moment. Okay, are you done copying?
Yeah, I'm done.
Okay, try to solve this and then I will do this with you. Yeah.
Upon the
Okay. All right. So let's read the question. An astronaut standing on the moon's surface throws a rock vertically upwards. The figure shows the speed time graph of the rock, where at t equals to 0 seconds, the rock just leaves the astronaut's hand. Air resistance of the moon can be neglected. Okay. And then we have this speed time graph. What is the time taken for the rock to reach its maximum height?
I put 0, right?
It throws, the astronaut actually throws the rock vertically upwards. So not really. Why will it be 0?
Because the speed is the greatest here. It's 6.5.
No, not really. It said what is the time taken for the rock to reach its maximum height? It's actually well, the answer says it's going to be the entire graph, because the distance that the rock travels is actually the area under the graph, and it is the maximum when it's over. So the answer will be 3.9.
How could you explain this again?
Yeah, so just a moment, let me see if I can mark this, hopefully now. Okay, so you have to reach the maximum height, that is almost the same as the maximum distance, let's say. Okay, and you can find this like under the graph, right? That is the distance. And as you can see, the rock will reach the maximum distance right here, which at 3.9 seconds. Yeah, so from the astronaut's hand, the rock will move upwards. And let's say the air resistance is negligible. And then it will reach 0, and then I think it will drop. But that is not in this graph.
On the graph, we just get to see how the rock is decelerating, right? It's going down.
Yeah, exactly. So it is deceleration. Yeah, so basically on this graph, you're actually just looking at the rock going up to its maximum height. Like I said, at the maximum height, the velocity, sorry, the speed will actually reach 0, and then it will start going down again. But that is not shown on this graph.
On the graph, we can just see the rock going up.
Yeah.
Then, shouldn't it have accelerated instead of decelerating?
No, because when an object is going upwards, the downward motion is the weight, right? So let's say on the moon, it's still going to be mg, but g of the moon, right? And then there is no air resistance. So I'm just going to remove this one because there is no air resistance. That's why, because it's trying to move up and then the force is actually trying to pull it down. That's why it's a deceleration.
If air resistance was to be there, then we could have called it acceleration.
Yeah, well, if the air, so that if the air resistance was higher than this weight, then it would have been acceleration.
Yeah.
Now the thing is, trust me, you'll learn this in the next chapter. This is all about the forces chapter. Right now, you don't have to know this, okay? Because it's a different chapter. The connection between force and acceleration, you'll learn it in the next chapter. Okay. Okay. Just a moment. Okay. Yeah, so about this, I know it's a bit confusing, but you'll learn about this force and acceleration in the next chapter. But just know that because, okay, why my pen is like that? Okay. So because there's only downward gravity and there is no force going upwards, yeah, this is actually deceleration.
Yeah.
Because this object is trying to go up. It only has that the force with which the astronaut is throwing it upwards, it only had that. So because of that force, it's going upwards. Okay.
Yeah.
So as it's going upwards, it will actually reach a point where it is zero velocity. So that's this point. And then later on, the speed will actually start increasing again, as we will see in the next chapter. And then you will actually see a graph like that. But that is not here. Okay, so it's only showing you half of the picture. I'm sorry for this confusion, but yeah. Okay, so
Yeah.
yeah, can you try number 2 now? I guess the total
Yeah, it's
distance traveled by the
the
rock.
area of the triangle, right?
Yes.
Yeah, I
So-
did it. It's 13. I got 13.
Mm. How much?
I took half into 4 instead of 3.9. Maybe that's why I got a whole
Oh,
number. Instead of
okay, yeah.
just
So
a point.
3.9
I
times
got
6.5, I think.
yeah, I got
Okay.
12.675.
Okay. Now, like I said, this is only half of the picture. This is the distance that it travels until it reaches the maximum height, right? So when it comes down, that's when it gets to its initial position. And the question asks that what is the total distance traveled by the rock when it returns to its initial position? So this area, this should be multiplied by 2.
By 2, yeah.
Yeah, so this multiplied by 2. So that is the answer.
But if they had asked for displacement, I would have only written 12 point. The answer we got
Yeah.
was right.
No, that's the thing. Like if they say what is the displacement of the rock when it returns to its initial position, then it's 0. Because it started here and it came back here.
Yeah.
Yeah. So I'm just going to write it as well. Displacement is 0. And this is the distance. Okay, next question. Find the acceleration of the rock. Now, obviously, this is the slope of the graph. That's when it is actually it's decelerating, so it's going to be negative acceleration. So don't forget the sign, okay?
So
Okay, try
I
to
can
find it.
just use the V minus U by T formula, right?
Yeah, sure. You can use that.
Yeah, I got minus 1.67.
Yeah, that's perfect. Okay, so that is going to be, I think, 6.5, right? Divided by
Isn't going to be 0 minus 6.5?
this one. No, that
Your
is
final.
6.5. Yeah, so
Yeah,
the final minus initial, and then the time that is going to be minus though.
Yeah.
Okay, that's how you get minus 1.67 meter per second square. Okay. Yeah, the next question. The rock is then brought back to the Earth's surface, and the astronaut repeats the same action as on the moon. Determine whether the speed time graph of the rock when it is thrown on Earth will be different. Explain your answer.
It will be different, right? Because the gravitational pull is different on the moon and on Earth.
Yes. So there's going to be, how is it going to be different? So what will the graph look like? Yeah, so because obviously the G is higher on Earth, it's 10 meter per second square. That means the deceleration will actually be more, right?
Yeah.
So, oh, okay, but also we have to take into account air resistance, I think, because air resistance is not negligible on the Earth. So the speed of the rock will decrease at an increasing rate. So the deceleration of the rock will also increase as the speed decreases. So it will be like the previous graph that I showed you for deceleration. So it is going to look like this. Doing a different color, like that.
But the speed is increasing here, right?
No, the speed will decrease.
But in increasing order or not decreasing order?
The speed, just like the moon, the speed will decrease, but on Earth, the deceleration will actually increase over time. So as you can see the slope, the deceleration is increasing, okay? So so that's why it will look like, you know, a curve and not a straight line anymore. Yeah, this will be, you know, much clearer as we go to the next chapter. Right now it's a bit odd, but yeah.
I'm done.
Okay. Okay, the next, I'm just going to give you another example because this one was a bit messy. So I'm going to draw a graph which shows the speed of a car from the time the driver saw an obstacle on the road and applied the brakes till the car came to a stop. Okay. So the graph looks like this. This is also a speed time graph. This is 20. This right here is at 0.5 seconds. And this right here is 4.5 seconds. Yeah, that's it. This is at 0. Okay. All right. The question is, how long did it take the driver to begin applying the brakes after seeing the obstacle? That is question number 1. Number 2, calculate the distance before the brakes were applied, and B is while the brakes were being applied. And finally, calculate the average speed of the car. This example is probably more suited to this chapter.
The first one is 0.5 seconds, right?
Exactly. This is 0.5 seconds. As you can see, this is where the speed is constant. And then the distance.
And the distance before the brakes is 10.
Yeah, so 20 times 0.5, this one. So this is 10 meters. And what about while the brakes were being applied?
And that's 40. Half into 4 into 20.
Okay, half into 4 into 20. That's right. How much is it?
It's 40.
Okay, that's 40 meters. So that's the area right there. Great. Next, calculate the average speed of the car.
Apu, is it 40 plus 10 divided by 4.5?
Exactly. So this is 40 plus 10 divided by 4.5. That gives us, I think, 11.1 meter per second. Okay. Great. I think we're done with kinematics, and now we can start dynamics, which will clear things out even more. These two chapters are very related. Almost all the questions will have both the chapters like together. So yeah. Are you done?
Yeah.
Okay, great. So let's begin dynamics. What is this chapter about? This is everything about force, okay, and how this how forces actually affect the speed, acceleration, and everything. Okay. Now, if what is the definition of a force? So it's a push or pull exerted on a body, right, by another body. Okay. Now, even the objects which are at rest, so which are stationary, they have some sort of force acting on them. Okay. It's not like they're not experiencing any force. Okay. So, for example, let's say an object sitting on a table. This one is also experiencing some force. So obviously the weight, its own weight is being put on the table, and from the table surface, there is another force going upwards, which is counteracting its weight. That is the normal force. Okay. Now it's important to actually see where I am starting each arrow. So as you can see, normal force, I'm starting it from the base of the table. Why? Because this is exerted by the table on the object, and the weight, I actually drew it from the middle of the object because that's where we actually have to draw weights from, okay? This is what we call the center of mass, this point right here. This one, this is the center of mass, or CM. Okay. Now what happens when we exert a force on a body? Effects of the force. One thing can happen, that is, it can increase or decrease the speed of a body. That is, it can make it accelerate or decelerate. And another thing can happen, that is, it can change direction of a moving body. Okay, so actually have to know that force actually affects the acceleration, not really the speed. And then this acceleration basically affects the speed, okay? Okay. Now, we actually need to know the 3 laws of Newton. So what is the first law? First law of Newton. A body will remain stationary or in continuous linear motion unless it is acted upon by a resultant force. Okay. Now this one, resultant, is a very important word. Now you could have asked me that why is this stationary then? Because even there are forces acting on it, the resultant force is 0. Okay. So yeah. Now the second law of Newton. This is basically the equation F equals to ma. This is the resultant force on a body. This is the mass of the body, and A is the acceleration. F and A are, so if the force, okay,
The force and acceleration will always. So I'm done copying too.
okay. Next is the third law. For every action, well, action, I mean force, there is an equal and opposite reaction. There'll always be a counteractive force, okay, that will try to stop the other one. Just like here, the normal force is trying to